Hi guys, so today's video we're going to be looking at trends of the periodic table, and in particular we're going to look at the atomic radii and how it's calculated, and then we'll look at the atomic radii of all of the elements on the periodic table and what tree. So the first thing that I want you to remember is what's the definition of radii. So from geometry we know that the definition of radius is the distance from the center of a circle to a point on the outside of the circle. And for the most part, it's pretty easy to calculate and find. We have a circle, it's got a distinct beginning and a distinct end. We could also find the diameter, which is from a point outside the circle through the center, hitting the other side. In other words, it goes all the way across. So we're going to take that and we're going to use that to look at the atomic radii. So here's a picture of the hydrogen atom as seen through a scanning tunneling microscope. And one thing I want you to notice real quick is that the atom is not perfectly circular, and it is those distinct outside we talked about is not quite there. And since that distinct outside is not there, scientists have had to come up with a different way of finding out what the radii of a element atom is. So here's another quick example before we look at what scientists have discovered. So here is a picture, again, as I showed you before, of the hydrogen atom. And again, just to look, it becomes very hard to measure from here out to the outside, because the question becomes, where do I actually stop? It looks like almost in this picture like a bunch of little triangles, so you're like, okay, well, where do I find that point? Because here it's right here, but here it's out here. So let's see what scientists decided to do. So what scientists decided to do, because of that funny exterior boundary line, is they decided to take and look at two atoms of the same element that were bonded together. So we've talked about our diatomics. We've talked about hydrogen and how hydrogen is found combined, if not combined with something else, then it is combined together with itself. Or fluorine, chlorine, bromine, all those different ones. So let's just suppose we're taking one of those, and maybe we're doing hydrogen since we've talked about it. And we have a hydrogen atom bonded to a hydrogen atom. Chlorine atom bonded to a chlorine atom. And what we've done, if you look at this picture, is they have found the nucleus of both of those, and they measure how far it is from nucleus to nucleus once it is bonded together. And then they just take that number and divide it by 2. So the atomic radius is defined as 1/2 the distance between the nuclei of identical atoms that are bonded together. And again, it is due to that electron cloud fuzzy exterior. Okay, now that we know how to find the atomic radii, let's talk about the pattern that we're going to see. And the first pattern we're going to look at is going across the period. Across the period. So let's just dig in a little deeper and see what that trend is. Okay, so one of the easiest ways that I think to explain to you how the trend goes. Now we're going to be looking at going across the periodic table, so from left to right. Okay, so in particular, we're going to look at this row right here. Okay, now one thing that you'll remember is that this is energy level 1 field, and this is energy level 2, energy level 3, energy level 4. Now we don't really care about all of them, but we're going to look at energy level 2, which means that in terms of our electron configuration, all of the electrons that are going here are filling an energy level 2, which means that the distance, okay, is going to be the distance, let's just say, from the nucleus is the same. Okay, so let's just say that piece of it. So here's an example, tug of war. I have a nucleus. So here's my nucleus. This one has 2 in it. This one has 4. This one has 5. This one has 6. Again, I'm just going across the periodic table here. But what's happening is that my electrons, of course, this is my first energy level, and that's got 1, and this is my second, my second energy level, and it's got 2 in. I can't draw a circle. And so if you look at the distance from those 2 to these 2, because those are the outside 2, and then we're going to compare these 4 to these, and these 4, now, I guess there's 3 there, and then these 6 to these 6. Okay? When you're looking at it, that distance all the way through is exactly the same. Think about a tug of war. These are 2 big guys. Remember that your protons are 2,000 times heavy, right? And your electrons are like little fleas out here. So you've got 2 big guys. They're pulling these 2 fleas, and that's as far as they are apart. Is that going to be very hard? And then you've got 4 big guys pulling. These 2 are here in the middle. They're between the 2. You're pulling. Here's 6 guys trying to get these. Basically, you're pulling these 2. And then you've got these 6 guys, or that's 5, and these 6 guys that are pulling them. If you've got 2 guys compared to 6 guys basically pulling these little fleas, hopefully you realize that these 6 are going to be pulling a lot harder than the 2. And the fact that outside in this outer energy level, yes, we're increasing electrons, but remember, in terms of the force pulling, you've got a lot more force here pulling than you would ever have here. So what happens is, because there's so much more force here, this here's a piece of cake. Okay, they're going to win in nothing flat. These, yeah, they're going to win. Might take a little bit. These might take a little less time, and then these, it's going to be a piece of cake. They're going to yank, and those electrons are going to come jumping at it. That's why, in terms of size, it gets smaller and smaller. So because the distance from the nucleus is the same, but we're gaining protons, then it is going to get smaller from left to right. Okay, now let's look at the next case, going down. Okay, so this time we're going to be looking going down. Again, n equals 1, n equals 2, n equals 3. Those again are my sublevels that are getting full. So in this case, okay, you've got hydrogen, which has 1 proton, okay, but it's also just got 1 electron. Okay, go here, 1 electron, my coloring. Okay, but now I have the next one, and again, it still has, this one is lithium, and it's going to have 3 protons, and so it is still getting more protons, but look what's happening to the electrons. Those electrons, that 1 electron is now out here in energy level 2. So even though I have more people, the distance here is getting larger and larger. And so then I go down to my next one, which is going to be sodium, which has 11. Which is a lot, right? But what has happened now is that 1 electron is way out here. Okay, so again, when we're talking the force pulling, we have increased that distance so much that really these protons could care less about this electron, right? These are up close, okay, right next to each other. Woohoo! Yeah, I'm going to get you. There we go. Okay, but here's this set of protons. That distance has got further that they're like, oh yeah, it's not worth my time. By the time that one is way out here, they could care less. And by the time I'm out here, I have my, again, my nucleus. Yes, it has got long, but now that negative is way out here, and nobody really cares. They're not even going to give it a second glance. And that's why, as you go down, we get larger. We're going to get larger. And again, it has to do with the increase this time in distance. So remember last time the distance stayed the same and we got more positives attracting. Now we've got the distance so far that distance does not make the heart grow fonder in terms of protons and protons and electrons. Okay, let's look at one more thing real quick. So let's just read through real quick the book definition. Atoms tend to be smaller the further to the right they are found across the periodic table. So again, as I go across, I am going to get smaller. The trend to smaller atoms across the table is caused by increasing positive charge of the nucleus, which attracts the electrons towards it. Because again, the electrons are all the same distance away from the nucleus. And then the last one is atoms tend to be larger the further down they go, and that trend is due to the increase in the size of the electron cloud. So now again, those electrons are getting further and further away, so the protons could care less because they've got so far away. They're like, yeah, go ahead and go on. Okay, so that is my trend. Now you're going to need to use that trend to answer the following question. Of the elements, magnesium, chlorine, sodium, phosphorus. Okay, and this will pause. You need to tell me which one has the largest atomic radius. So line them up in order from the largest to the smallest. And again, explain your answer. And let's see if you got the correct answer. Sodium is the largest because of the fact that it is in the third period. Sodium has the largest, the lowest atomic number and is the first element in the period. Okay, so sodium is the largest.